We worked on improving the aerodynamics of a side channel blower, and we worked at Stevens Institute of Technology in New Jersey. So what is a side channel blower? You guys might know it as a pump. So it's basically a pump that transfers gas contents or liquids, but we mainly dealt with gas contents. It was first introduced in 1996.
So basically, as you can see the diagram over there, there's an inlet port where it comes in, as it says. So the impeller, which is basically the center, starts to rotate. So that's basically the axis, and as the axis begins to rotate, the impellers over here begin to rotate as well. And of course, areas on the outside move quicker than the areas on the inside. And it goes through here, and there's various exits for it to come out. But the main bulk of the object comes out from the outlet port, which is closed off over here right now. It's usually open, but in this diagram it's closed. So it's causing, as it comes in, the pressure is low and velocity is high, and while it comes out, velocity is low and pressure is high.
These are diagrams of the side channel blower that we use. This is a right side view of the blower. This is a front view, and this is a back view. This one right here is an isometric view. It's pretty much from top left-hand side. These are the inlets and the outlets. They have pretty much similar design, except that one is used to take the air in, and the other one is used for the air to come out. I would like to mention some factors that you guys should know. So centrifugal force. Basically, centrifugal force is caused when something rotates in a circle. In this case, the shaft is what rotates in a circular motion, and when this happens, the liquid pushes out. Velocity and pressure are inversely proportional, and the entering gas / air, the pressure increases the efficiency of the pump, meaning that the pump already has a certain amount of air in it. So when the pump intakes some air, the entering gas in the pump doesn't mix with it. So this causes the entering gas to push the air that was just taken in through the outlet channel.
The side channel blower, it's not evenly spaced out. As I was showing before with the diagram with the inlet port, it's actually smaller than the shaft, and that's so that if you have a smaller area for the liquid or the gas to move through, then the velocity is going to increase. However, as it goes into the larger area, the velocity decreases and the pressure increases due to the larger area to move through. And basically when it comes back to the smaller area, it's able to move slower.
We try to optimize the design of the side channel blower. So basically we try to make changes to the existing design, and what we did was we tried to improve the volume of the air, the amount of air that's moved per minute. We also try to get a higher rate of flow, meaning that instead of making the shaft rotate faster, which is going to need more energy, we were looking for other ways for the air to come out more quickly without the shaft moving faster.
Like for example, with the pump that we were working with, the Siemens Elmo G200 pump, basically there's a silencer in the inlet port so that it doesn't make as much noise, but as I was talking to our mentor, Dr. Choi, on this, he told us to take out the silencer because if you were to take out the silencer, you'll increase the efficiency rate. So that was one of the main things that we did in our new model.
Basically, when we increase the impeller speed, it's going to increase the power range. The power range depends on the rotations of the impeller per minute. Another factor that we focused on was improving the centrifugal force. As I mentioned, centrifugal force is caused by the rotation of the shaft, and we try to take advantage of that, and we try to improve that.
Yeah, concerning the centrifugal force, there's not only one exit for the liquid to come out, liquid or gas. Actually, in the shaft, there's various areas because since the liquid in the outer area moves the quickest, since you want the liquid to move as fast as possible, usually there may be a hole in the shaft so that the liquid towards the inner areas of the shaft is able to come out at a faster rate. So we tried, when I say we improved the centrifugal force, we tried to decrease the amount of shafts, or we tried so that we could have more liquid moving at a faster rate. So yeah, we basically used Pro Engineer, which is a CAD software, which stands for Computer Assisted Drawing. And that was basically, so we designed the model of exact dimensions on Pro Engineer, and then we use the ANSYS CFX, which is a simulation program, and that's, it's able to take the diagram that we made, the model that we made, and with the model, it simulates the various forces like the centrifugal or the axial energy. And as I was saying before, we use the Siemens Elmo side channel blower or pump for the more commonly used. And it was a G200 series.
So procedure basically was what he said. So we use the Pro Engineering software interface to design the shafts and the rotating axis. And we use the ANSYS CFX interface to analyze the design, which means that using the software, we pretty much simulated the airflow and saw how it comes out.
It also gave us numerical values concerning the different forces. So basically, there was a certain rates per minute that it gave us, which is actually around 400, so we were trying to increase that rate by at least 100 or so.
What we also did was we tried changing the design of the impeller using Pro Engineering software and also using SolidWorks. The outer body of the blower and the position of the inlet and the outlet of the airflow. So our basic purpose was to improve the aerodynamics. So these were all the steps we did to see which one improves the airflow best.
Yeah, so basically these are two examples of the inlet and outlet ports on Pro Engineer. So as you can see in the photos that we had before, these are the yellow sections which were basically blocking off the two inlets. And as you can see, they're basically identical to one another. So by doing that, it's actually allowing it for the gas or liquid to come out at the right rate. And they have holes over there, so that that's one of the areas where the entraining gases go through. So,
This is a cover that protects the shaft. It's basically metallic, and this is the design of it.
Yeah, basically when I was talking before about the shaft, this is the shaft over here. And this is the inlet side and that's the outlet side. And the reason why we have the cover here is so that it acts as like a silencer in a way, because that's where the impellers would be. Because when the gas and liquid are coming through, they never touch the impellers. The impellers are just using the pressure, the air that they're making to affect the shaft, if that wasn't clear before.
These are references and acknowledgements. Students Institute of Technology, Dr. Chang, he was our mentor, Rajesh, Ishan, Burton, Harlem Children Society, and Dr. Sad. Any questions?
You talked about getting higher rate of airflow, but you said without increasing the speed of the rotation. I was wondering how that's possible.
Because if we were increasing we were trying to increase the rate, but we weren't trying to increase the speed that it was moving, because the problem was that we were trying to have the energy efficient one, and if we were to increase that, that would increase the power input. And that's why we were trying to decrease the amount of holes that we were having in our shaft. So it wasn't really a problem of increasing or decreasing the dimensions or increasing the energy flow. It was more of really tinkering with the design.